But why that is happening? So someone's seeing these shapes, trying to say that okay, there is some kind of concept which is happening here, and these are some geometric objects which you see all the time, circles, ellipses, and all these things, right? And you want to see how many times they intersect. Can you predict something like that? So this is very geometric object which you see in all around you. So let me draw one more. So let me draw this circle. So these two parallel lines also, this circle and this line. Okay. So there are plenty of concepts. So here these two lines do not intersect at all, and same here. So how to understand these things? These are geometric objects. We want to understand something. The first thing we want to do is that we want to understand this problem. We want to first of all parameterize these things, these lines, this circle and everything. We want to see how we can look at them as algebraically, right? Something to hand off where we can compute some things, right? Here right now we just have intuition in our mind. Intuition is good for mathematics, but we have to, when you want to prove something, you need something to work with. Okay, so let us see. So these are two lines. This is x equal to y. This is x equal to minus y. Yeah. So if you take two elements, real numbers, and add them, and they become 0, then they will be on this line. Is it okay? You know graphs and everything. You might have seen these kind of things. And this is again x equal to y line, and this is a circle equation, x square plus y equal to 1. Right? All those real numbers which satisfy this equation will be on this. Okay? And so on and so forth. So these are the equations for these two curves, and similarly here. Is it okay? Here also you can write the equations. This is circle, this is line, and two lines. So can you see the pattern now? Anyone can guess the pattern? Know what are the number of intersections? Anyone wants to guess? So here is it. So here you are just working with x and y. X and y are variables. You are adding them, you are multiplying them finitely many times only. Okay, and then looking at the a comma b kind of elements in R2 which satisfy those equations. Okay, that's what we are doing. So here you just have x and y, degree 1 things, right? In both these equations, right? And then you are getting that you are intersecting just 1 point. Is it okay? Here you have equations, again both are in degree 1, but they are not intersecting at all. Okay? Again let us go here. You see 2 here, 1 here, and multiplying them you are getting 2, right? And these are the 2 points which you might get. You might get, because this may also happen, right? Yeah, so on and so forth. Let's continue. This 2, 2, 4, 3, 2, 6. Yeah, so you can see the pattern now. Yeah, so the expectation is if you take some geometric objects which are defined by these kind of combinations, some combination of two variables like x4 y5 plus 10 times x cube y square plus say 11 is 0, and you take x plus y equal to 0. So if I intersect these two things, how many points will I get? At most. So here I will add these two things up, I will get 9, here it is 1, so at most I will get 9 points. Yeah, so that is a prediction one can make by seeing these objects. Is it okay? Yeah, so this is what basically geometry tells you, or this, just looking at these pictures one can guess something like this after some time. But guessing is a different thing, and so guessing will make you state such a statement. Okay, but proving is a different thing. So due to lack of time we will not go into the proof at all. Okay. So okay, so let me just give you a very small proof in some sense. So what is happening here? Let us look at these two equations and try to see why this 9 comes into picture when you intersect with a line. Is it okay? So if suppose what I am trying to do, I have this my curve C1, this is my curve C2. So, two curves. So, more precisely, what is my C1? C1 is all those points in real number such that if I take a power 4 b power 5 plus 10 times a power 3 b power 2 plus 11, this I am getting 0, right. You can do it with any powers, any integers. You can play this game. C2 is a comma minus a. Right? If I add these two things here, they will become 0. Yeah? And we want to understand what is the intersection. What do I mean by this? I mean a comma b such that first this equation is satisfied and my a is equal to minus b, right. These three equations I want to satisfy. Now, suppose a is equal to minus b, what will I do? I will just put minus b here, a equal to minus b in the first one, right. What I will get? B power 4 times b power 5 plus minus b power 3 b power 5 plus 11 equal to 0, right. I will get this. Now, look at this equation. This is b power 9 times b power 8. It is equal to this equation, right. I am just multiplying the coefficients. Is it okay? What is the degree of this polynomial? This thing is this, exactly this number, maximum number. It is 9. Yeah. Now, to prove this statement which I said here, that the intersection will be at most 9, you need a theorem which says that, is again a statement which is non-trivial to prove, it is not completely trivial, that if I take a polynomial of this polynomial, then it will have at most 9 roots, which means there will exist at most 9 distinct b which will satisfy this equation, okay, and those are exactly the intersection points. Yeah, that is why this number comes. Is it okay? This is a simple example. This is just an example I gave you. C1 and C2 are fixed. Right.
Degree is producted.
Right.
You have written addition.
Yeah, no. So, yeah. So, degree of this C1 will be 9. This is addition in this, like it is a maximum degree which you take the addition of these 4 and 5 in one curve.
Oh.
And for C2 it is 1.
Okay.
Yeah.
Right.
Okay. With me? So, this is just a very first example. What I want to convey just in 2 minutes, that to prove this statement you have to consider all curves C1 and C2 which are distinct. It is again a non-trivial thing. You have to go to abstraction a bit, you have to do some theory and then prove this. It is not an easy statement. Never take it, any statement in mathematics is not usually an easy statement. Okay, if you see the proof, it looks easy. Like even if you look at these diagrams, this looks trivial, like okay, geometrically I know that this is the intersection points. This is how it should be. If I give you arbitrary things also, yeah, but it's not the case. Okay, and this diagram tells you why I made these two things. This diagram tells you that okay, it's always equal to the product. In these examples are, but these two examples tell you that it may be less than equal to also. Okay, fine. How much time I have? Is okay? Okay, so 5 more minutes. Okay, then. So okay, so let me now question this. So these are just one observation. Like in mathematics, I love to say that in sciences also, and usually you see a concept, you develop a theory, you make such a statement, and do you stop there or you want to wonder what is next? Okay, so what you can ask is, so here there is an inequality, right? So you can ask, is it like you are missing some points? Like when you are looking at this diagram, you know that they are missing a point, right? What is the point you are missing here? Point at infinity, right? These things, you know that this, I guess you guys know, right? Parallel lines meet at infinity, whatever that means, right? So if you can make sense of infinity, you can add this point, and then you can make a very general statement that two lines meet at a point. Yeah, you may not be able to see it, okay, but they do meet somewhere. Is it okay? Good. So this is one example, but not that. So here, yeah, again. So this is the one example which I just draw here also. Here, so let us try to solve this equation very quickly. So this is x square plus y square equal to 1, and my x is equal to minus 2. That is given to me, right? This is this line, x equal to minus 2, y is arbitrary. Okay, if I substitute it here, what I get? X equal to minus 2, I substitute here, 4 plus y square equal to 1, y square equal to minus 3. Yeah? No, it's like square root of minus 3. Yeah? So here the problem becomes that you know that usually if I square a real number, it is always a positive number, right? I can talk about root 3 as a real number. I hope that you guys know real numbers. Yeah? Have you heard about complex numbers? Yeah? No? So there are something more, a bit more, where you can take this root 3 and what we call as root minus 1. You just add this, just think this as some imaginary number, okay? And that's what we call iota basically, it's written. Okay, so there is some concept you can enlarge your real numbers to get more zeros, okay? That's what is happening in this example. You go to something called as complex numbers, you will learn in the time. It's okay if you don't know right now, it's completely fine. Then you get some points of infinity which you can add. Plus what can happen also, that even if there is a one point, so this point is a bit different than meeting at one point. So this point which I have denoted here is one point right here. This is a bit different than this point. It's touching the circle. So when it touches, we will call it, it kind of it's here that it's two multiplicity. Okay, so there is some concept of multiplicity comes into picture also, not just that it's hitting or not. Okay, so these are the examples. You see these beautiful pictures. Here the multiplicity is again 2. Yeah, I will finish this. So this is again multiplicity 2, 2. I will add 4. 2 and 2 multiplication 4. Correct number I am getting, right? You can see this again. This is 3. So again 2, 2, 1, 1. So I will get 4, which is here again 4. Right? Here I am getting 1 point, but with 4 multiplicity. Yeah. So this tells you that there are 3 more ways to get more points. 1, adding infinity. Second, adding complex numbers, looking at solutions in complex numbers. And third is counting how many times it should appear in the intersection. Okay? And that gives you the last theorem, which says that if you take two distinct points, look at these points with infinity. Okay? This is the point with infinities also, and then you are working with this complex numbers, then this is actually equality when you compute the multiplicity also. So it does become equality there. Okay? When you look in the correct word. So you should always ask which word you should look into some equations. Okay? I will finish here.
Thank you, Professor Gupta.